Okay, we now know that the high temperature limit, the classical limit, is obtained rather well. Everything goes to the classical result. The thing that we have done before. And the important thing is what happens when the temperature drops. Let's look at that limit, which is the quantum limit. As temperature of the system falls, of course, lambda T cube over V is no longer small. It also grows. If that is the case, you cannot use it as a quantity in terms of which we can expand our thermodynamic properties. So we have to use, well, of course, expansion is not useful. We have to use the full expressions. For example, actual expression, n over v is 1 over lambda t cube, g, the Bose-Einstein function of z. We have to use this expression. We shouldn't try to expand it in terms of a small quantity. Well, of course, at the beginning, the total number of bosons are all in the excited state. And we are interested in when the ground state will be occupied. The occupation of the ground state will start. Excited state, E stands for the excited states, and that's where the energy is not equal to 0. This is the case when Z is not equal to, well, it's not coming close to 1, isn't it? Z equals 1 is the opposite limit, where everything goes in the ground state. Well, important occupation of ground state begins unless Z equals 1. So n equals n excited if you are not in that limit. Now let's look at the quantities, the way they behave. If you look at it from a graphical point of view, I think it will be clearer. The chemical potential, for example, as a function of temperature, behaves as follows. Always negative. And this difference is of the order of 1 over v. When you look at the Bose-Einstein function, let's draw it normally like this. G 3/2 z, that's what we had as a function of z, goes like something like this. Z1 is the important value, goes more or less like that. So it is continuous and it has a bound at z equals 1. It is a constant value. It has a specific value. This value, when z equals 1, that means G trias 1 is 2.612. Has to do with Riemann zeta function, as I'm going to write explicitly soon, but that's the value of the Bose-Einstein function when z equals 1. Z itself has this form. Here is z as a function of v over lambda t cube. It starts from, well, low values, and it goes to 1. As it goes to 1, see, it remains 1 after certain z equals 1 value. So at that value, when it is 1 over 2.612, this difference is of the order of 1 over v again, very small. So in between 0 and 1, this G 3F Z increases monotonically with Z and is bounded, as I told you, the greatest value being 2.612. Well, that is known as zeta 3Fs. That is Riemann zeta function. Okay? What is it? Let's remember once more. G 3F1 was 1 plus 1 over 2 3Fs plus 1 over 3 3Fs, etc. That series has that value. Okay? Well, we see that for all values of z of any interest, for all z, for all z of interest, that means between 0 and 1, we have the following property. G3 of z is either smaller and at most equal to zeta 3s. That means 2.612. Okay? It is, give me the z in between 0 and 1, I'll tell you what the corresponding g is. From the graph you can read it. Okay? And maximum value, this value, is 2.612. Well, for given V and T, for any volume of the system and at any temperature T, then you can write the following for excited number of bosons in the excited state, and E is always smaller than or equal to this number that tells us what the maximum G is. V times 2 pi m kBt, explicit form of lambda T cube, zeta 3 hours. Isn't it? That's the maximum value. You can also look at this as the maximum number of bosons the excited state can hold. If you increase the number of bosons above this, the rest must go into ground state. That's the Bose-Einstein condensation. And the ground state has an unlimited capacity. You can put as much particle as you like in it, as many particles as you like in it. So that's our important limit. Let's look at the number of particles in the ground state. Well, total number minus the excited state. Number in the excited state gives you the number in the ground state. Let's write the number of bosons in the ground state as N0, which is N minus this number, isn't it? N minus V 2 pi m kBt, 3 hours, h cube, zeta 3 hours. Now let's look at the precise value of the Z. So we are in the interesting limit. We are getting our condensation. Precise value of Z can be determined from N0 plus 1, which can be written as 1 minus 1 over N0. Well, almost 1. That was the interesting limit. That is Bose-Einstein condensation. Now, one important note, this Bose-Einstein condensation is taking place in K-space, isn't it? It is not happening in direct space, coordinate space. So it's happening in the K-space, means it is nothing but particles going into the ground state, bosons going into the ground state in large numbers. Let's look at the onset of condensation once more. the particle number should be greater than V T3s. Well, I have written that case for the excited number in the excited states. V3s 2 pi mkb h cube. This is 3s zeta 3s. This is the condition for the onset of the Bose-Einstein condensation. That means the excited states are full. Whatever you increase above it must go into the ground state. Now, one important thing about this total number, it must be constant, okay? If it varies, you won't have the condensation. Now, if you hold N and V constant, vary the temperature. This is one way of looking at the transition, simply because when you lower the temperature, you go into the quantum limit and condensation comes out. If you have T going rising, you go to the classical limit. If you vary the temperature, you can get the condensation. One way of looking at condensation is in the temperature range. You can also go into V and play with V, lower it, increase it, and see what happens to the system. But let's vary temperature. That's what experimentalists also do. See what it means to the onset of the Bose-Einstein condensation. So in this case, temperature must be lower than a critical temperature that corresponds to, I am always playing with the same expression, writing it in different forms, which is h squared 2 pi mkb n over b zeta 3s 2/3. Well, Tc is the characteristic temperature for the onset of the Bose-Einstein condensation. You should get below that, or the condensation starts at that temperature when you start lowering it. Okay? It is characteristic temperature. For T lower than Tc, what do you have in hand? You have a two-phase system, isn't it? Two phases. Well, if you take those in the excited state, one phase, those in the ground state, another phase, it is a two-phase, two-phases system. Your system can be looked upon as a normal phase, particles in the excited state, where NE particles, number in the excited state, NE, which is equal to N T over TC 3Fs particles in the excited state where the energy is not equal to 0. Okay? The condensed phase is the second phase, important phase. Where it consists of N0 particles, which is total number of particles minus the one in the excited state. And here's the picture showing these numbers in two phases, number of particles in two phases. It is like this. Temperature in terms of some critical temperature or characteristic temperature. And here's N0 over N. And numbers in the excited state, it is something like this. And 0 over N is 1 growing after T is smaller than Tc. Can we see this clearly? The value 1 is where T equals Tc, where the important condensation starts. Okay? Characteristic temperature for the system. As the number in the ground state increases, as you see, the number in the excited states start to drop. When total number is fixed, that's what should happen, isn't it? When is the whole number of particles in the total number of particles in the ground state? When N0 is equal to capital N, isn't it? That is when N0 over N is 1 at that point. In between, you have a two-state, two-phase system, isn't it? There are some in the excited state, there are some in the ground state. Mixed state, in other words. Do you have any questions with this? About this characteristic temperature, all the particles are in the excited state, isn't it? There is nothing in the ground state. So if you keep the temperature of the system above Tc, you have all of the particles in the excited state. When the occupation of the ground state starts, you have the Bose-Einstein condensation. Okay, let us. There is a singularity at T well equals Tc. All of a sudden, the second phase starts. Well, at T equals Tc, or T going to Tc, from below, try to understand what I mean by this. N0 over n, number in the ground state, is 1 minus T over Tc to the power 3s, or approximately 3 over 2 Tc minus T, Tc. When T equals Tc, that's 0, isn't it? Exactly the picture. It is 0 at T equals Tc. It starts growing afterwards when it becomes smaller than that. Okay. Now we can study the thermodynamics of this system, the condensed or two-phase system. For example, pressure-temperature diagram of the system can be studied, the specific heat can be studied. You can study all of the properties again. PHYS terms, you can study everything from thermodynamic point of view. Here is PT diagram. Have to get the expression to plot that. P over kBT, we know the start. It is 1 over lambda T cube, G 5/2 Z, in terms of Bose-Einstein function. Do you have any questions up to now? Are you following? Yeah. So the pressure can be written in terms of temperature, if you like, as 2 pi m h squared. Keep the constant terms. Write the temperature term in kBT form. 5/2 G 5/2 Z. For V greater than the minimum. Now, what is V minimum? Can you play with volume per particle or interparticle distance? Of course, I told you the critical quantum limit is when the thermal wavelength is of the order of interparticle distance. Okay? So instead of using this exact expression of 2.612, you just use the condition that the quantum effect becomes dominant at lambda t equals to A, which is V, small v to the power 1/3, then you can get the condition for Bose-Einstein condensation, onset of Bose-Einstein condensation. Okay? Very simple physical thinking. So, I'm not going to do explicit calculations here. For V smaller than V minimum, we have P at Tc, if you like, 2 pi m h squared, 3 hours, kb Tc, 5/2 zeta 5/2 with z equals 1. G 5 half 1 is exactly this zeta value, isn't it? 2 point, oh, 5 halves is different, 3 halves we know, 2 ones, 2 6 1 2, but that thing is 1 3 4 2. Riemann zeta function. Now, P, tell me, by looking at this, tell me something about the pressures in condensed phase. Does it depend on volume? Is there volume in the expression? No volume, is temperature dependent thing, isn't it? It's independent of volume. Independent of volume. What does that mean physically? If it is not depending on volume, this means what for the gas? It is infinite compressibility, isn't it? What was compressibility? 1 over V del P, isn't it? If P is independent of V, you get 0. Huh? 1 over 0 is infinite. So compressibility is infinity. Extremely important. I think you should always look at this as not an exercise in mathematics. Of course, you have to do it, but you have to interpret the results physically, or in terms of physics of the problem. Well, this PTC, using what TC is, you know the value of TC. I have written that for you. Inserting TC in that expression, pressure at TC becomes zeta 5 halves divided by zeta 3 halves n over V kV TC, or in terms of numbers 0, 51, 34, n over V kB TC. It is not like classical gas, isn't it? PV over NKB TC is 1 in the classical case. So this is like half of that value. So this is of the order of 1/2 the pressure of the Boltzmann gas. Can you tell me the physical reason for this? Why is this decreasing? I told you this in my earlier lectures, because when you put particles in the ground state, it is P equals 0 state, they don't contribute to pressure, isn't it? That's why drops. I think you have to concentrate on this a little bit more. Everything should be dried. Let's look at the specific heat of the system, of our gas, boson gas. More or less, we have done the condensation, but let's look at the specifics. Some more thermodynamics. Here is the specific heat or heat capacity of the gas. For T smaller than or equal to Tc, that means condensation. Well, we have to use the following, Cv and Kv. 1 over, well, we have written this before, 3 hours d dt Pb and Kb, keeping the volume constant. For Pt, you can use Kbt over lambda T cube, zeta 5 hours. If you do that, you find the following. (15 over 4). Why don't you do this? Zeta 5 hours V over lambda T cube. So the whole thing is proportional to T to the 3 hours. So at the characteristic temperature, or in the language of phase transition, the critical temperature, you have the following. Cv at Tc over NKB is 15 over 4 zeta 5 hours divided by zeta 3 hours. That is of the order of 1.925. What is the classical value for this thing? Huh? What is U? N times 3 over 2 kBT. Take derivative with respect to temperature, you have 3 over 2 NKB. So divide by NKB, you must have 3 over 2. 1.5, it is bigger than that. Isn't it? Interesting. Higher than the classical value. which is 1.5. Now for temperatures bigger than this characteristic temperature, we can also find it separately. For T greater than the characteristic temperature, CV over NKV becomes derivative of this quantity with respect to temperature. At constant volume. So that comes out to be, please check this, G 5 Hertz, Z. When Z becomes 1, the second term goes to 0. So the whole thing, this is for higher temperatures. We have the following pictures then. This picture of heat capacity or specific heat, units of NKB, is something like this. Exaggerate a little bit. 3 hours. 1. For low temperatures, it goes like, here it is T to the power 3 hours. Above 1 at high temperatures, it drops, as you can see from the expression. Whenever C has a maximum or a cusp like this, you should get excited. I know you never get excited, but you should sometimes. Some results are more important than others, isn't it? You should know the time to get excited. Do you have any questions? Let's discuss the physics a little bit.